Welcome to Lesson 7. In Lesson 7, we're going to take a look at the stoichiometry of precipitation reactions. So what you notice there in my first statement is that calculations occur the same way for precipitation reactions as they do for other reactions. So calculations, they say that they occur the same way, but really there is one glaring difference. And that difference is this introduction of molarity as a conversion factor. When we did all of our other stoichiometry reactions or calculations before, we used molar mass, grams per mole. But now we have a new kid on the block. We are going to use moles per liter as our conversion factor. But that's the only thing that's different. We also need to go through the mole to mole ratio in order to come up with the answer. So let me just walk you through a couple of examples. Example 1 says calculate the mass of solid NaCl that must be added to 1.5 liters of a 0.1 molar AgNO3 solution to precipitate all the Ag plus ions in the form of AgCl. Again, I tell you this, don't let all the words bug you. Look at what the chemicals are: NaCl, AgNO3, AgCl, Ag plus ions. And then decide, okay, what are reactants and what are products? It says that we are going to react NaCl to AgNO3, and we're going to get AgCl as one of our products. So let's write that down. NaCl plus AgNO3 gives us AgCl plus question mark. Well, what are the only things that are left? If Ag went with Cl, Na must go with NO3. So what I like to do is I like to then put the information that we know underneath the species that we're speaking about. So we know that we are going to take 1.5 liters of 0.1 molar AgNO3. And we want to know how many grams of NaCl it takes in order to get AgCl out of it. So really, we aren't trying to find out how much AgCl we're going to get, so that's not our question mark. What we are trying to find out is the amount of NaCl that reacts with AgNO3. You've done this before. The only difference is when you've done it before, we've talked only about doing this with solids. Now we need to deal with their concentrations. So let's take a look at this. Look at our given. We're given liters and we're given molarity. So your first question to yourself might be, which one do I start with and why? So let's take a look at this. Liters is a simple measurement. Molarity, though, doesn't really make for a good conversion factor or a given, but moles per liter does. So what you should notice is that molarity is really just a conversion factor that's given to you in the problem. So keep that in mind. When you're looking for your given, you're looking for the thing that's either in liters or moles. Molarity is a conversion factor. It's not a given. All right, so let's start with our given. 1.5 liters AgNO3. How do we get from liters to moles? We use molarity. 1 liter of AgNO3 gives us 0.1 moles of AgNO3. Now, how do we get from moles to NaCl? Our mole to mole ratio. The coefficients for AgNO3 and NaCl are both 1. So it's a 1-to-1 ratio. So we simply write that out. And now that we know how many moles of NaCl would have to react, we can calculate the mass of NaCl. So 1 mole of NaCl, we know, weighs roughly-ish 58 grams. So, of NaCl. If we then go through and cancel out our units, you'll see that we are left with an answer in grams of NaCl. The answer for this, if you do all the math, is roughly 8.7 grams. So this means that it would take 8.7 grams of NaCl poured into 1.5 liters of AgNO3 solution, that is 0.1 molar, in order to get all the Ag ions to become AgCl. So you need to kind of visualize this as well. Think about what this would look like if you were in a lab. How would you go about doing this? And understand that these numbers aren't just numbers in a math equation. They represent something. So try to visualize the labs or the experiments as you're trying to go along. Let's take a look at the second example. It says when aqueous solutions of Na2SO4 and PbNO32 are mixed, PbSO4 precipitates. Calculate the mass of PbSO4 formed when 1.25 liters of 0.005 molar PbNO32 and 2 liters of 0.0250 molar Na2SO4 are mixed. That's just a whole lot of chemicals going on there. Fortunately, a lot of them are actually repeats. So let's take a look at this. It says that we are mixing Na2SO4 with PbNO32. So Na2SO4 is added to PbNO32. And they want us to calculate the mass of PbSO4 that's formed. So we know that PbSO4 is one of the products. You should then try and figure out what the other product would be. Hopefully, you come to the idea that the Na and the NO3 are still floating around in there, so you get NaNO3. You need to balance the equation, so you need to put a 2 up front, and everybody's happy. Now, why don't they tell us that there's NaNO3 left over? Because don't forget this is in solution, and we know that nitrates are soluble. So the NaNO3 really is not taking place in the reaction. They are what we call spectator ions. Spectator ions. They sit back and they watch the action. So they have the ions and the compounds that take part in the reaction, and then you have the spectator ions that sit back and watch. All right, so let's take a look then at the numbers that they give us. They give us 1.25 liters of a 0.05 molar PbNO3 solution. All right, put that underneath there so that we know what we're talking about. Remember that the 0.05 molarity is really just a conversion factor. And then it also says, though, that we have 2 liters of 0.025. And again, that's a molarity, so that is a concentration. What are we looking for? We're looking for the mass in grams of PbSO4. So what happens to this? Well, this becomes a limiting reactant problem because you're given 2 beginning numbers and you're expected to come up with how much is going to happen in the end. So this is just like when you did the stoichiometry in Unit 3. You're given 2 reactants, 2 numbers for those reactants, and you're expected to calculate how much of the product you're really going to get. So what you're really going to do, here's 2 separate problems. You're going to do a problem with Na2SO4, and you're going to go to the PbSO4 to calculate how much you could get. And then you're going to start with the PbNO32, and you're also going to calculate how much PbSO4 you could get from that. And then whichever one is the least tells you how much PbSO4 you're going to get. The one that produces the most ends up being the non-limiting reagent, and the one that produces the least is the limiting reagent. And I'll go through that again once we're done. Let's just do the math here. If we start with Na2SO4, we had 2 liters of that. In 1 liter of the Na2SO4, we have 0.025 moles of Na2SO4. Our mole to mole ratio says that for every mole of Na2SO4, we will get 1 mole of PbSO4. And then we need to do a little math to figure out how much PbSO4 weighs. And if you do that math, hopefully you will find that it weighs 303. I could be wrong, but I believe that's what it is. So when we do all of the calculations, all the multiplying and all, well, you divide by 1, but when we do all the calculations, we get 18.94 grams. So that means, given that amount of Na2SO4, there are enough sulfate ions in that Na2SO4 to give you 18.94 grams of PbSO4, assuming you have enough lead coming from the lead nitrate to react with it. So let's find out if there's enough lead coming from the lead nitrate to give us 18.94 grams. All right, so we start with what we're given, 1.25 liters. In 1 liter, there's 0.05 moles. And now this is where we have to be careful. I really should be labeling these with the compounds. But we know for every mole of PbNO3, 2, there's a mole of PbSO4. Again, we know that 1 mole weighs 303 grams of PbSO4. And when you do all of that math, you get 15.1 grams, assuming I did this all right, of PbSO4. So what this means is, given those starting amounts of PbNO3, there's enough lead ions to contribute to get 15.1 grams of lead sulfate, assuming you have enough sulfate to react. So now the question becomes, how much will you actually get? Well, hopefully you can see that lead 2 nitrate must be our limiting reactant, because we can only get 15.1 grams of lead sulfate with that amount of lead ions. And so we will end up with 15.1 grams of lead 2 sulfate. So hopefully you see the parallels that are occurring here between the stoichiometry in Unit 3 and then this new stoichiometry that's occurring with our new favorite conversion factor, molarity. So just keep in mind that instead of starting with grams and going to molar mass to get to our mole-to-mole ratios, we're going to start with liters, use our molarity to get to the mole-to-mole ratio to get to grams at the end. Otherwise, every other process is the same. This is just a different application of stoichiometry using molarity instead.